All right, welcome back. Maybe with an additional cup of coffee. Our next speaker for this morning is Mao Zeng, and he will tell us about conservative and radiative binary dynamics from Amplitudes. Mao, take it away.
Okay, thanks for the introduction, and thanks for the wonderful opportunity to speak here. I'll talk about our recent work on calculating state-of-the-art post-Minkowskian approximation for binary black hole dynamics using modern scattering amplitudes and multi-loop integration methods developed for collider physics. The work is in collaboration with Julio Martinez at Caltech, Enrico Herman at UCLA, and Michel Roof at Freiburg University, based on 3 papers in last year and this year. Start with some introductions, then I'll tell you about our machinery for getting post-Minkowskian expansion results, starting from reusing post-Newtonian calculation methods. Then I'll talk about the very new frontier of going beyond conservative dynamics to radiative dynamics using the formalism of Cassava-Maybe-O'Connell and the collider method of reverse unitarity. I'll show our main result, which is the complete third post-Minkowskian binary dynamics, including a conservative energy loss and radiation reaction effects. For the introduction, needless to say, we know that gravitational waves have been a tremendous discovery in recent years at LIGO/Virgo. And in future decades, we have a lot of new detectors coming up, both space-based and ground-based. Taking ground-based detectors as an example, in a few decades' time, the sensitivity on the log 10 scale will improve by several orders of magnitude compared with recent LIGO runs. Well, while theoretical predictions are okay for LIGO, they will need vast improvements to match the future sensitivities of the experiments. The most well-known perturbative method to calculate binary dynamics, at least for the regime where the black holes are far separated, is known as the post-Newtonian expansion. It has a very long history, not long after the invention of general relativity. So you expand in both the coupling constant, which is normalized to be gm/r, and the velocity v squared. If you use Virow's theorem or the explicit circular orbit formulas, these 2 quantities are of the same order of magnitude. So the expansion necessarily involves both higher orders in g, higher orders in v squared, or mixed terms with both certain orders in g and v squared. Another perturbative expansion with a long history, although it's received a lot of revived interest in recent years, is the post-Minkowskian expansion. Here you only expand in the coupling constant gm/r, keeping exact velocity dependence. So at least this aspect is exactly analogous to what we do all the time in relativistic QFT calculations. We expand in coupling constant. But traditionally, both because of the inherent difficulty and because of maybe a lack of attention, the progress has been very slow compared with the post-Newtonian expansion. So before our recent new results, the best result was from Westphal in 1985, who worked out the scattering angle of 2 black holes in a hyperbolic encounter. So here there's the order g term, that's the leading order. Then there's the order g squared correction, known as the second post-Minkowskian correction. But both terms have exact dependence on velocity, which is expressed through the dot product of the normalized velocities of the 2 incoming black holes. So the main topic is a new method from scattering amplitudes. You will also hear talks from Carlo Heisenberg and Michael Solon on applying scattering amplitudes to the binary problem. We have seen many methods developed or in active development, which allows you to extract classical physics out of quantum amplitudes. For example, Eichner exponentiation, non-relativistic effective field theory, or an observable formalism, which bears lots of resemblance to Kleider methods because you define some measurement operator based on the S matrix. This will be the main method used in this talk. And now if we transition to the purely classical regime, there's also something neat. We can take gauge invariant scattering observables, which are defined for hyperbolic like orbits, observables like deflection angles. So it turns out that these observables encode also bound state dynamics, which is more immediately relevant for LIGO and other gravitational wave detectors. There are several methods to translate between hyperbolic and bound state dynamics, for example, by matching to effective one-body Hamiltonian, matching to EFT potential, or through a direct analytic continuation, also known as the boundary to bound dictionary, invented by Kellin and Porto in 2020. And for the scattering amplitude aspects, there are challenges for both the loop integrand and loop integration. The integrand method, the integrand aspects is taken care of by generalized unitarity, which is a bread and butter method in modern scattering amplitudes research. There's the double copy, which gets gravity from Yang-Mills. And there's also improvements you can make to Feynman diagram-based methods using nonlinear gauge fixing to reduce the size of the intermediate expressions. And for the loop integration, there are many modern methods originally developed for particle physics at colliders, which we have imported into gravitational wave physics to great effects. So just to give you an idea about the progress, so the post-Newtonian expansion, as I mentioned, have a long history, and 4PN, an impressive order, was completed in 2014. And recent years have seen exciting partial results at even higher 5PN and 6PN orders. And due to the lack of space, I apologize for not acknowledging this enormous body of literature here. For the post-Minkowskian expansion, we have Westphal's seminal results from the 1980s. And just 2 years ago, Zvi Byrne, Clifford Chang, Radu Royban, Cha-Hsien Shen, Michael Solon, and myself obtained the third post-Minkowskian potential between two black holes, limited to conservative effects in this paper. And we saw that the methods were rather easy at this order. So we went to the next order in just 2 years in a paper earlier this year. And I should mention that there's a wood-line EFT method by Raphael Porter and collaborators like Gregor Kellin, Zhengwen Liu, and Dilapa. So this method is perhaps more closely connected to a purely classical calculation, and they've reproduced both results. Now, going beyond the conservative sector, a very new frontier is radiative dynamics in post-Minkowskian expansion. Compared with the conservative sector, the radiative sector inherently starts at higher orders in G Newton. In fact, it starts at order G cubed, i.e. 2-loop order, because you have to get an acceleration before you can radiate. This field is in a way much more recent. Already there have been several results produced by this line of research. For example, in the conservative third post-Minkowskian result for the scattering angle between two black holes, there was some puzzling divergence at higher energies. And by now we understood that this divergence is artificial and is cancelled by radiation reaction, computed both using classical GR methods by Thibaut Damour and by scattering amplitude methods by two groups, including our group. So another question is that what's the energy loss in a hyperbolic scattering as the leading order G cubed, but keeping exact dependence on velocity? So this question attracted interest since the 1970s, but it's not until our paper that a result was obtained which kept exact functional dependence on velocity, drawing lessons from scattering amplitudes and from Kreider methods like reverse unitarity. And there's many other aspects like angular momentum loss and going beyond the so-called inclusive observables to more fine-grained observables like waveforms, as well as progress to even beyond order G cubed by many recent papers, all published this year. So now I'll talk about our apparatus differential equations, which somehow gives you a way to upgrade post-Newtonian calculation to a post-Minkowskian calculation. I should just mention that the combination of double copy with advanced modern loop integration methods have been a very powerful combination, which solves several questions like the UV behavior of n equals 8 supergravity at 5 loops and 2-loop 5-point amplitudes in n equals 8 supergravity involving some of the same integrals as 2 to 3 scattering in QCD, as you heard from Simon Badger yesterday. So going back to the main topic, for gravitational wave physics, the main amplitudes of interest are scalar to scale, scalar goes to scalar plus scalar 4-point amplitudes, as well as 2 to 3 amplitudes, 2 scalars goes to 2 scalar plus extra graviton radiation. To calculate these amplitudes exactly, it's very hard. And it's essential to use simplifications from taking classical limits. But I should mention that there's also exciting recent progress in evaluating some of these integrals, mostly in the planar and in the equal mass M1 equals to M2 limits. They are actually the same integrals involved in Barbour scattering and muon electron scattering. And okay, and so to take advantage of simplifications of the classical limit, we will use the method of regions to obtain an asymptotic expansion of the amplitudes. So the amplitudes have a strange feature that they have a huge incoming momenta because these are macroscopic black holes, not microscopic particles. But if exchanged gravitons are extremely soft, because if you have some impact parameter B, by a simple Fourier transform, the dimensional analysis tells you that the wave number is the inverse of the impact parameter. And then the actual momentum exchange is of order h bar over B. So the exchange momentum in the T channel is order h bar suppressed compared with the incoming momentum. So we are working in the limit that the exchange gravitons are very soft. The method of regions developed by Benneke and Smirnov is exactly addressed for this kind of problems. For classical physics, the necessary region we need is the soft region. We do a Taylor expansion in the limit both Q and L the loop momentum are much smaller than the external momentum. And we do a Taylor expansion before we integrate over full domain to get the soft expanded result. As many of you know from QCD and soft theorems, for example, after the soft expansion, the exact momentum dependence will degenerate into the dependence on normalized velocities. And in fact, these integrals will only non-trivially depend on the dot product of the normalized velocities, u1 dot u2. So this is the kind of the gamma factor or rapidity separation of the collision. And so we will have non-trivial dependence, for example, polylogarithms or even more complicated functions in this variable. To efficiently tackle this kind of calculations, we imported the well-known method of differential equations, which were very successfully applied to Collider physics. We imported into post-Minkowskian gravity in the paper last year. And subsequently, it was already widely adopted in many calculations at both 2 loops and 3 loops. The basic idea is that you first do the soft expansion to eliminate non-trivial mass dependence. And now the integrals only non-trivially depend on velocity. Then you write down the differential equations of the Feynman integrals with respect to velocity. And solving these differential equations will give you exact amplitude, will give you amplitudes with exact dependence on velocity. And there's a powerful method of canonical form of differential equations, which was inspired by the uniform transcendentality of n equals 4 Superyan Mills amplitudes introduced by Johannes Hahn. And there are automated packages which can transform arbitrary differential equations into this canonical basis. So it turns out that the same differential equation we applied can be applied to several physical contexts by just changing the boundary conditions, but not the differential equations themselves. If we calculate the boundary conditions in the potential region, we will obtain results localized on matter poles, and that will give you conservative dynamics. If you calculate these soft integrals without further expansion on conventional integration contours, that will give you the full result incorporating radiation reaction correction to the two-body dynamics. And also you can calculate phase space integral instead of loop integral. So in the Casalvo-Maybe-Ocano formalism, these phase space integrals will give you observables like total radiated energy and momentum. So if you localize integration on these phase space delta functions, again, the differential equations are unchanged, but the new boundary conditions will lead to these exact results for phase space integrals, which we applied to get the 3 p.m. accuracy energy loss for black hole collisions. So the K-Mock formalism is a formalism based on scattering amplitudes. So it's an in formalism. You calculate S matrix, both virtual amplitudes and cut amplitudes. So you have in states transitioning to out states by the T matrix, and you insert operators, for example, a total radiated momentum operator between the out states. So, and in this formalism, we obtained a phase space integrand by cutting the virtual integrand. And the actual integration is taken care of by the method of reverse unitarity, which was a very successful method for Collider physics. Many important results, for example, Higgs total cross-section at NNLO, and more recently at N cubed LO was obtained by this method. And there are also other applications like energy-energy correlators in electron-positron annihilation obtained using the reverse unitarity method. The basic idea is just that phase space delta functions can be rewritten in a way which is very similar to ordinary propagators you encounter in loop integrals. So the operators well known for loop integrals like integration by parts, differential equations, they are completely unchanged except for boundary conditions. So, and applied to our case, the master integrals for energy loss in black hole scattering at the leading G-cubed order, there are only 6 master integrals to calculate. In fact, 5 of these master integrals shown on the right can be simply obtained by Katkowski rules, because for each of these 5, there is only one Katkowski cut, and the integral is just equal to twice the imaginary part of the virtual integral, which we already calculated for the purpose of the two-body dynamics without energy loss. There is just one integral which has more than one Katkowski cut, and this for this one we use the differential equation method enabled by reverse unitarity. And the boundary condition was also very simple for this method. We just had to do some power counting in the method of regions to obtain the boundary condition near the static limit.
Now you have 10 minutes left. Okay, thanks.
Now jumping to the result for the radiated energy. In fact, the full result for the radiated form momentum. And the radiated form momentum is proportional to the sum of the 2 normalized velocities. And there's a bunch of prefactors also, and multiplied by a dimensionless energy loss function. It contains special functions, actually just logarithms at this order. There's the arcshine, which you may be familiar with from the 3 p.m. conservative result. But if you normalize the, but if you rationalize the square roots, as you often do in multi-loop calculations, this arcshine is actually also a logarithm. And I'll briefly mention that the superclassical terms, which are encountered in conservative calculations, are also encountered in our calculation, but they cancel after a sum over diagrams. So the result is remarkably simple, given the standard of modern scattering amplitudes, where you deal with polylogarithms of weight 4 or weight 6 or even above. But it's also remarkable that this is this result is obtained for the first time using the modern methods. And our energy loss result passed a lot of checks, which unfortunately I'll have to skip. But there's a vast body of literature which allowed us to compare in various limits. I'll mention that besides energy loss, we also worked out a complete 3 p.m. dynamics, including radiation reaction. So here we just need one more spanning cut compared with the conservative case. And for the cubic Feynman diagrams, we go from 7 to 10, taking advantage of recent nonlinear gauge fixing methods, which also simplify Feynman diagram-based calculations. So the master integrals for the transverse impulse, which is basically another name for scattering angle, roughly. So 15 master integrals were needed for the conservative case, and there are a few which drop out for various reasons, and there are just 3 or 4 master integrals needed, which should be calculated in the soft expansion, which are needed to get the radiation reaction part of the answer. And we have many tricks using the K-Mock formalism. There are simplifications using cutting roots and diagram symmetries. And the final result for the radiation reaction was cast in a form which is very similar to Eichner calculation. It's a real part of the 2-loop amplitudes minus lower loop iterations like the tree cubed contribution. So in the latter paper this year, we obtained the complete 3 p.m. accurate impulse during hyperbolic light scattering for black holes. We reproduced the potential region, the conservative result in the earlier 2019 paper, which was done with non-relativistic EFT, we reproduced the result using the K-Mock formalism. We also reproduced it in Eichner formalism because once you have the full dimensional regularized integrals, it's easy to use either of them. And the new results are the total radiated energy and momentum, as I mentioned, and also the radiation reaction, reproducing results from Damour and from another group, De Vecchia, Heisenberg, Russo, and Veneziano, and we find full agreement. So in conclusion, scattering amplitudes have now gone beyond conservative effects to deal with radiation effects. In fact, the amplitude methods are addressing the full spectrum of questions in binary dynamics, including also spin and finite sizes. And there are many Collider methods which we have successfully imported into GR calculations. We have established the equivalence of several competing approaches, NR-EFT, Eichner, and K-Mock for 3 p.m. conservative and radiative dynamics. And there are various directions, for example, exploring connections to linear response theory of classical GR, and thinking more clearly about how to optimize amplitudes, given that classical physics are localized on matter poles. So this ends my talk, and thank you very much.
Thank you very much, Mao, for a nice talk. Are there any questions for Mao? David Broadhurst.
So congratulations for using these tools for hadron colliders, for black hole colliders. It's wonderful. But what is striking, and you remarked on it, is the simplicity of the transcendental functions that you have, only logarithms, arc-sine logarithms, and yet you're using a machinery from particle physics that is polylogarithmically rich. So do you expect polylogarithms to appear at higher order?
Yes, in fact, they already have. So my talk has concentrated on radiation effects, but just for conservative effects, it was already calculated at the higher 3-loop order. So at 3 loops, the transcendental weight has just gone up a little bit. Mm-hmm. The 3-loop result is of transcendental weight 2. I think actually Mikhail Solon will talk about it tomorrow. The 3-loop result also has complete elliptic integrals of the first and second kind. So you can imagine at even higher orders, more complicated transcendental functions will yet appear. And the modern methods for these polylogarithms and elliptic integrals will find many applications in the near future.
I'm very glad to hear that. Thank you.
Okay, thanks.
Gustav?
Hello.
Hi, Mao. Thanks for the really nice talk. So one thing I'm aware of when you're looking at radiation reaction as opposed to just the potential region is you have to include these so-called mushroom graphs, these additional contributions that you didn't have in just the potential region. Can you say a little bit more about the structure of these graphs, what they look like? And I don't know, I guess gives just some kind of an intuition as to how you can see that those terms are related to radiation.
Okay, yeah. So the mushroom graphs, they are like a graviton connecting the same matter line to itself. For example, this cut diagram here, graviton is not going from line 1 to line 2, but just going between line 1 itself. And so actually all the extra Feynman diagrams beyond the conservative case, they are mushroom graphs when you draw them in a good orientation. So they are absolutely needed for both radiation reaction and energy loss. For example, in fact, these mushroom graphs are even super classical. They give you contributions which do not have a smooth classical limits, and they only cancel after you add up all of them and do the necessary subtractions.
I guess
yeah.
my question is there an easy way to see if I work in the potential region and integrate these graphs that they just give 0?
Oh, yes. There's a good way. So if you take a mushroom graph and expand the gravitational momentum in the potential region, then you will get integrals which are scaleless integrals, and they just vanish in dimensional regularization. But it's no longer the case when you do a soft expansion without further expanding in the potential region. So there's a simple way to explain why they vanished before, but not now when you include radiation.
Okay, thanks.
Okay.
Are there more questions for Mao?
I have one, maybe, if I may.
Yes, if it's a very quick one.
It's well, depending on the answer, I guess. So you said that you are using this expansion by regions, looking at soft regions and potential regions and so on, and also that you're using the method of differential equations. So my question is, how well do these two actually go together? Sort of, is it the case that soft regions only couple to other soft regions through these differential equations, or how does that work out?
Our basic setup is we always do the soft expansion first. And now after that, we have these so-called soft integrals, which we now calculate using differential equations. A slightly subtle aspect is that the differential equation can be also applied to further expansions in the potential region, because the further expansion commutes with IBP and it doesn't change the differential equation and only change the boundary conditions.
Okay, thank you.
Okay, thanks.
Right, we are a little short on time, so let us thank Mao again.